Okay, so next what we're going to do is we are going to focus on the practice problems for correlation, linear regression, and ANOVA. So first let's go ahead and let's open up our copy of R if we don't have it open already. And we're going to run through each of the practice problems. So the first things first, just like we've been doing each time, let's make sure that we have our data open to the right file. So just go ahead and find where your data are located. Make sure that you move your working directory to the correct folder. And then once we have it all opened up and set up, we can run through and we can make sure that everything works properly. So let's go ahead, and once we have it all set up, we have that data 2 open just like before. We'll go ahead and let's go through those practice problems. All right, so for the first question, what's the correlation between BMI and meters walked at final? So first thing that we have to do is we're going to have to open our data set at time point 3. That's the final time point. And we'll just call this data set final. And then we can just do a correlation between the BMI and the meters walked at final. And again, just keep in mind that because there are missing observations here, so as you can see, there's a few people with missing observations. If I were to not include this na.action command, then this is not going to, this may have some issues with running. So what I do is I just run na.action, and that just makes sure that everything is working. Now, it seems like it's fine right now, but sometimes it may or may not work. So it's always good practice to always make sure that you include na.action equals complete.obs. And that just means that you're going to only use complete observations. It's going to be a list-wise deletion of any observations that don't include both the BMI and the meters walked. And you can see that down here with the degrees of freedom of 32. That means that 8 observations have been deleted, and this is because those 8 observations either don't have BMI at final or they don't have they don't have meters walked at final. Okay, so next up, let's go ahead and we're going to make a scatter plot. And we're going to make a scatter plot of age on the x-axis and BMI on the y-axis at time point 1. So again, let's just create a baseline data set. So again, we're going to take baseline at data 2, we're going to input time point 1, and we're just going to plot baseline of BMI as the y and baseline of age as the x. And then we should get a plot that just looks like this. All right, so for our next practice problem, include a regression line on in your scatter plot, make it blue, a vertical line at mean age in red, and a horizontal line at BMI equals 27 in green. So for this, again, within this scatter plot that we have, we are just going to go ahead and we're going to add a regression line right here in blue. And so that's all that is. It's just AB line of BMI of regressing on age, or age regressing on BMI, excuse me, and it's in the color blue, so it shows a negative correlation between baseline age and BMI. And we can actually just take a quick look to make sure that this actually seems to hold up. And the way we could do that is we can just run a correlation looking at baseline. And it's always good practice to look at these things to make sure that what you're seeing for your actual regression lines are actually what the data represents. So you should always try and make sure that you're seeing things in the correct directions, in reality. So as we can see here, there's a slight negative correlation of negative 0.15, and so that seems to hold up. So we know that that regression line is in fact accurate. Next, let's go ahead and let's create a vertical line at mean age in red. And so all this would be is, again, we're going to create a vertical line at the mean of baseline age. So here we just do that. And as we can see, again, baseline age was about 71. So we've got that vertical line right there. And then if I wanted to create a horizontal line at BMI of 27, then all I have to do is I have to put H equals 27, because it doesn't matter that I have to input the BMI command. I can just say that I want a horizontal line at the number 27. And so that will give us a horizontal line, and it will be in green. All right, next up, number 4. So this one's a little bit easier. It's only going to be one line of code that we're going to add. And for this, it's going to be include a lowest curve on the scatter plot. You want a black dotted line and make it much larger than your other lines. So in order to do that, we're just going to use the command lines, and then we're going to use lines and in parentheses lowest, and then baseline age, baseline BMI, because we're creating a lowest predictive line based on the relationship of age with BMI. And the line type is going to be 3, so that's just going to be a dotted line of some sort. And then the line width is going to be 6, so it's going to be quite, it should be in theory at least quite a bit bigger. But since I have a little bit of a command issue in there, that might be why it didn't show up properly. But now, as you can see, when I put in the correct line, the correct command LWD, then the line is a lot bigger. Okay, now we're going to go ahead and we're going to make a new scatter plot for the 5th question. So let's just go through that. So for this question, okay, so now let's go ahead and let's make a new scatter plot. And for this, this time we're going to have ADAS-Cog meters walked at midpoint. However, this time see if you can get separate dots for each group, that is for INT and for control group. So this is a little bit more complicated. I did say that you might need to Google this, and also I want you to see if you can make separate regression lines for the intervention and the control group. So we're just going to walk step by step through each of the individual points of this. So first things first, just like before, we're going to have to create a new data set only for midpoint. So for this, I just use the subset command, and I just put it at time point 2. From here, it makes sense as well to also subset intervention and control. So I'm going to subset the intervention group, and I'm going to subset the control group. So there's going to be a separate data set for each of these groups at that time point. So as you can see, 20 observations in the control, 20 observations in the intervention group, and there's 40 observations total at midpoint. All right, so now in this instance, it might be a little bit easier to create a new command or a new, a new set of variables for the treatment group. For this, what I'm just going to do is I'm just going to relabel group into TX, and that's just going to have a 1 or a 0 attached to it. So it's just a slightly different way of having intervention and control labeled. So what I'll do first is we're just going to go ahead and we're going to make that basic plot that we're interested in terms of looking at plotting the meters walked versus the ADAS-Cog or predicting ADAS-Cog plus performance or ADAS-Cog performance. And so here we can see how this would look. We have IC and INC, so I represents intervention, C represents control. So one way of approaching this would be that I can just put PCH, and that's going to and equals midpoint of group or midpoint at group, and so that's going to give me those labels of I and C for those individual groups. But I might also want to add some other things to that. So for instance, I can add some other stuff in terms of labels. So for instance, if I want to have a label for the intervention group and the control group, this is going to provide an AB line just for the relationship for the intervention group, and it's going to be in blue. And this is going to provide another regression line for the control group, and it's going to be in red. So there's clearly a different relationship between meters walked at midpoint for the intervention group as compared to the control group. I can also do a few other things perhaps if I'm interested. So let's just go ahead and let's go back to the initial graph of this, and I'm just going to delete those graphs just for a second. And what I can do is, instead of using group, I'm now going to use TX. And so as you can see, because this is labeled as 0, 1, these just have different shapes. So we have circles versus squares now for the individual plot points. And using that same idea again, I can create those regression lines. And then I can also create a legend in here that will make it a little bit easier for me to tell what's a intervention person versus what's a control person. And actually, believe it or not, this gets even easier when we use something like ggplot too. So for right now, we're just going to stick with using the plot function. But the good news is that this becomes even easier when we're using something like ggplot. We can do a lot more cool stuff with ggplot in particular. Okay, so next up, let's go ahead and we're going to use performance analytics in order to get correlations in a histogram for BMI, age, and ADAS-Cog at final. So we're just going to go ahead, we're going to get the library for performance analytics. We're going to create this data set called final.chart, which is just a subset of final. And that's just going to have the columns that are related to those variables. So again, if we want, we can just go to columns, call names or final, and we can just go ahead and we'll count those out. So 1 is ID, and then 9 is BMI, 4 is age, and then we have 8 is COG, and that's it. So those ones will do it for us, and we'll just go ahead and we're going to create that data set, and then we're just going to use that chart.correlations that we were talking about earlier, and then we get this nice plot looking at both the correlations between variables, but also the scatter plots and then the histograms of those variables in particular as well. Okay, so for question 7, we were looking at, is there a significant difference in ADAS-Cog between males and females at final, and what's the t-value and p-value? So easiest way to do this would just be to do a t-test. So we can just look at ADAS-Cog, and we would just do the t-test of that, and we can see that there is no significant difference at final between ADAS-Cog based on biological sex. We could do this as well using ANOVA if we were so inclined. So for that, we would just do LM, ADAS-Cog, and then sex, and then final. And this would get us to the exact same spot. So in this case, you would need to specify, though, ANOVA, and then we'll get to the same place. So again, the p-value is 0.55, and it's about roughly the same thing depending on whether you're using ANOVA or a t-test, but roughly the value is the same. Okay, question 8. Is there a difference between males and females when we control for age at final in ADAS-Cog? And so for that, how we would do that individual question is we can just look at the f value and the p value for this as well as the question asked. So let's just go ahead and we'll run through it. So we're just going to create this linear regression looking at ADAS-Cog, wherein we're going to regress sex and age onto ADAS-Cog at final. And so from here, we can either do an ANOVA.lm or we can do summary.ANOVA.lm. Either will get us to the same point. So from here, what it looks like is that there's no there's no sex differences in ADAS-Cog performance after accounting for age. However, what we do see is that if in terms of the relationship of age with ADAS-Cog performance at final, there is not a significant relationship, although it is looking like it is going in that direction to a certain extent. So it's close. So we can see that for age there is a there seems to be somewhat of a relationship. Perhaps it's a small data set that seems to suggest that as age increases, that ADAS-Cog score appears to decrease after accounting for biological sex, although this doesn't reach statistical significance. So then for question 10, does the model looking at sex differences meet the assumptions of ANOVA? And so in our last video, we didn't really touch on this, but the way that we can really look at assumptions is we can use a program called GVLMA. And what GVLMA does, and we can make sure that it loads, is if we don't have it loaded onto our package of R, we can just go ahead and we can use that that command of pacman to load it up. And once it's loaded and installed, all we need to do is we need to just go ahead and we would run through our model of GVLMA. So what that does is it looks at each of the assumptions of linear regression. So it looks at kurtosis, skewness, link function, heteroscedasticity, and we can also plot aspects of our model as well to see if it meets any of the assumptions of linear regression. So to do this, we just put in plot dot and then the name of the ANOVA model, and this gives us that residuals model, so we can check for independence, and we can also check for normality. We can also check the QQ plot, and you can see that there seems to be some issues in terms of the QQ plot in terms of our assumptions of normality, but it does appear that, at least for the most part, that there doesn't seem to be any real instances where it appears that we are not meeting the assumptions of ANOVA. So there doesn't seem to be signs of heteroscedasticity or anything along those lines as well. Okay, and then last but not least, our last question for this module is, do males and females have different education levels at baseline? To answer this question, we just do the chi-square test, wherein we are going to create this table looking at education based on biological sex, and then we can just run the chi-square, and as we can see here, there is no significant difference in education based on biological sex. And so this is really it for in terms of the main things I wanted to cover in this lesson right now. In the next one, we're going to spend a little bit of time going into discussing the ins and outs of data visualization, and get into the nitty gritty of how we can do a lot more cool data visualization using the tool ggplot2. So thanks for sticking around for this, and we'll see you in a little bit for the next one.